Hi, this is Sahar Liaqat, and I'm an engineering student in University of Engineering and Technology, Pakistan. The topic of my research is computer-aided detection of COVID-19 using chest imaging. Uh, COVID-19, coronavirus disease 2019, is a microbial infection that is induced by severe acute respiratory syndrome coronavirus 2, that is also called SARS-CoV-2. Automatic computer-aided detection can help detect the infected patients using chest imaging that includes chest X-rays and CT scans. This paper proposes a method to detect infected patients with high accuracy using X-ray images of a patient. It proposes a model that includes deep model features and local binary patterns and using support vector machine as classifier. The model is used for binary classification among COVID-19 and normal patients, and it produced 99.4% accuracy. Now, COVID-19 was uh, initially appeared in December 2019 in Wuhan, China. It turned into a global pandemic very fast. On March 11th, COVID-19 was declared a pandemic by World Health Organization, and COVID-19 appears as an extremely contagious disease, which is which is very critical for patients in critical condition. The mortality rate is high for patients in critical condition. It started spreading in many countries with its highest cases in USA, Italy, Iran, and Spain. In Pakistan, the Ministry of Health announced first confirmed patient on February 26, 2020 in Karachi, Sindh. Total infected patients in Pakistan have reached zero point 0.5 million approximately, and total casualties have reached 13,076, reported on 4th March 2021. Um, there is no confirmation of complete eradication of the virus as the vaccines are still under test. Symptoms of COVID-19 include high body temperature, pneumonia, respirational symptoms that are dry cough and shortness of breath, reduced count of lymphocyte, reduced white blood cells. COVID-19 detection methods include RT-PCR, that is reverse transcription polymerase chain reaction. This method is less feasible due to its high cost and poor sensitivity, which is around 71%. The other techniques for detecting COVID-19 are chest tomography or chest X-rays. Now, why X-rays should be considered? Now, CT scans are more expensive as compared to X-rays in many countries, and in developing countries, there is a lack of availability of CT scan labs in rural areas as compared to X-ray labs. Now, automatic COVID-19 detection can automate the scanning procedure, making it easy to detect the infected patients, and it provides the radiologists in medical decision making that includes disease diagnosis, tracking, and prognosis, and provides proactive safety of the medical practitioner through minimum contact with the patient. Hence, a rapid and automatic detection of infected patients is desirable using chest X-rays. These are some of the research work that we have gone through, and the findings of these research are following. This includes the improvements that can be further made are small dataset problem. Now, the small dataset problem can be solved by, of course, increasing the dataset that is being increased day by day, and if the data set is small, validation schemes and data augmentation can be used to avoid the overfitting problem. Increased false positive rate leads to misdiagnosis, causing overload on medical staffs due to falsely detected COVID-19 patients accommodation in hospitals. Area under the curve of model can also be further improved. The proposed method achieves maximum AUC and requires a low-cost system to implement the model without parallel computing with less computational complexity. The proposed model is shown here, which starts with the input image to the pre-processing part. Then the pre-processed image is fed to the LBP features extraction. After extracting LBP features, deep features are extracted, and when both features are extracted, both are concatenated and fed to the machine learning classifier. The first step, that is the image preprocessing part, includes contrast enhancement and image resizing. Now, why is contrast enhancement required? Here in X-ray images that are gray toned images have high amount of noise and low intensity, and boundary representation in X-rays is weak and poor. That makes it difficult to extract features from X-rays. X-rays, after enhancing the contrast, are give more accurate features. These are the steps that are used in the contrast enhancement method. First, the image goes through histogram equalization, then minimum filter, and after minimum filter, the complement of the image is taken. Sharpening filter is applied on negative picture, and histogram equalization is again applied. Mean filter and maximum filter is applied, and at at the end, histogram equalization is again applied on the resulting image. Now, here in the diagram, this is the contrast enhanced image of this X-ray image. Here we can see clearly a lot of features that are missing in this X-ray image. Enhanced images are then resized to RGB 224 cross 224 that is required by the VGG160 model. These are the after enhancing the contrast and resizing the image, LBP features are extracted. This is the mathematical expression of the LBP features. Now LBP, that is local binary pattern, is an efficient texture operator which labels the pixels of an image by thresholding the neighborhood of each pixel and considers the result as a binary number. Now, the reason of using LBP features is that it is the most simple and efficient texture operator. After extracting deep features, the LBP features, deep features are extracted. The VGG16 pre-trained model is used for extracting deep features. Pre-trained model, the VGG16 has 16 layers created by a visual geometry group from Oxford University. VGG16 was trained for weeks on ImageNet database that comprises over 14 million images with 1,000 classes, achieving 92.7% accuracy, ranking in the top 5 pre-trained models. Deep features are fused with the LBP features after concatenation. The dimension of deep features per image is 1 cross 1000, and for LBP features is 1 cross 50, making total of 1 cross 1050 features per image. This is the VGG16 model representing its layers with the showing max pooling layer, fully connected layer, and softmax layer. The classifier used is the SVM classifier. Support vector machine classifier constructs a hyperplane or set of hyperplanes in finite dimensional space, which can be used for classification, regressions, or other outlier detection. Now, a good separation is achieved by a hyperplane that has the largest distance to the nearest training data point of any class which is also called the functional margin, since in general, the larger the margin, the lower the generalization error of the classifier. This is the mathematical expression that is used for the SVM classifier. Here we have used Gaussian SVM classifier that has a changed kernel. The validation scheme used is the k-fold cross-validation scheme. We have used this scheme because the dataset is small, and to avoid the overfitting problem, this validation scheme is used. K here is the number of folds for validation method. Cross-validation is a method of resampling used to analyze machine learning models on a limited dataset. It is used to validate models on unseen data that provides more practical and general results without any bias, since fixed partition is not used. It also helps to obviate the overfitting problem for models that with small datasets. Here in the image we can see that K is kept 5 and the entire dataset is divided into some sections, and in every fold one section is used as testing part and the remaining are used as training parts. So by using this scheme, every section is used as training and testing. For the experimental setup, we have used a low-cost system for our experiment that avoids the need of parallel computing and GPU card. This is one of the positive point of this research. 8 GB RAM Intel Core i5 system is used without a GPU. MATLAB 2020A along with deep learning toolbox is used. The data set is used from Cohen. 125 anterior posterior images are taken from the Cohen dataset, and 500 normal X-rays are taken from the Kaggle dataset. Cohen dataset is increasing every day. It includes X-ray images and CT scans. The X-ray images of Cohen includes X-rays from different positions, the anterior, posterior, or lateral position. Now we have only used the anterior, posterior position of X-rays in our research. These are the evaluation matrix. Um, we have compared accuracy, area under the curve, and false positive rate for our result analysis. A confusion matrix is required to evaluate these metrics. Area under the curve is calculated by determining the area under the ROC curve. These are the expressions, mathematical expressions of accuracy and false positive rate. Here TP is true positive and TN is true negative, FP is false positive, and FN is false negative. For the experiment itself, VGG16 features have been extracted from the last layer of VGG16, that is the last fully connected layer, FC8, that produces 1000 pixels. And the SVM classifiers that were tested were linear SVM, quadratic SVM, cubic SVM, Gaussian, coarse Gaussian, and medium Gaussian. Now the model was trained with 30 iterations to acquire better results, and the results were compared with other pre-trained model results. These are the results of our experiment. These are the other pre-trained models with which we have compared our VGG16 along with deep features and its deep features and LBP features extracted. The best results were performed with VGG16, that is 99.4% accuracy, and area under the curve came out to be 1, and the minimum FPR was achieved using VGG16 with deep features and LBP patterns. The box constraint level is a parameter that prevents the overfitting problem. Increasing this parameter leads to a smaller number of support vectors and longer training times. Now, the lowest FPR 0.6 was achieved, and FPR for other models were very high as compared to the one with VG16. This is the ROC curve of the model. This AUC is computed using the ROC curve, which is the area under this ROC curve. AUC here is nearing the maximum achievable value, that is 1. AUC ROC curve is created by plotting the TPR against the FPR, that is true positive rate against the false positive rate. The curve demonstrates the trade-off between sensitivity, that is TPR, and specificity, that is minus FPR. ROC curve closer to the top left corner of plot represent better performance, which in our case is very close to the top left corner. Now, ROC is a more accurate measure as it does not rely on the distribution of classes, and it makes it more useful in medical image classification. In conclusion, this paper provides a model to classify between COVID-19 infected and healthy patients. The proposed model provides an accuracy of 99.4%. It can also be implemented on large data sets, and severity-based classification can be done on existing X-rays for getting in-depth condition status of patients by observing their X-rays. And this severity-based classification would help the risk stratification for examination of patient survival, forecasting risk position of patients, and predicting duration of hospitalization, which aids in patient population management for the hospital and provides an additional benefit of individualized individual patient care. These are the references of that have been used in my research, and thank you.